Hello and welcome to today's lesson. This is going to be the first lesson of hopefully a series teaching the A-level specification. The first lesson is going to be about discriminants and inequalities. So let's get started. The first part we're going to look at is going to be all about discriminants. So discriminants are related very closely to the quadratic formula. And of course, if you don't remember the quadratic formula, then please go back and recap. So the discriminant basically allows us to find how many solutions the quadratic has, but it doesn't actually tell me the solutions of the quadratic. So you might think, well, that's a bit useless. It's not. It's quite useful actually. And we'll be using this information to solve problems about quadratics. For a quadratic equation of the form ax squared plus bx plus c equals 0, we have obviously that the quadratic formula is this. The discriminant now is a piece, if you like, of this quadratic formula, and it's simply the b squared minus 4ac part, the part inside the square root. Some of the key things to understand are that when this discriminant has a value of greater than 0, the quadratic has two distinct solutions, two different solutions basically. When it's equal to 0, we have one repeated solution, and when it's less than 0, we have no real solutions. Alright, so let's look at when the discriminant is bigger than 0. We know that it has two distinct solutions now, but let's look into that in a bit more detail. Let's have a quadratic that clearly has two solutions as shown by the graph on the right. It has the solutions 0.382 and 2.618. We're clear on the fact that it has two solutions, but let's just see what value the discriminant is going to have. We're expecting it to be positive. Let's have a look. So if I substitute in my values, the minus 3, I square it of course, because it's the b. We subtract 4 lots of a, which is the 1 here, the invisible 1 if you like, and then the c is just this 1 on the end here. Let's simplify this. We get 9 minus 4, and that is obviously 5, which is definitely positive. So we know that when it has two solutions, the discriminant is definitely positive. Let's try and reinforce this idea. Let's think about splitting up this fraction. We have minus b over 2a plus or minus the second fraction. So we split it up into two fractions, and then we consider if the part inside the square root is positive, then the second fraction, the one in red, cannot be equal to 0. It has to be something other than 0. Because if the discriminant is positive, and we square root this number, we get another number, and we divide by 2a, we still get another number. So this definitely can't be 0. And so we add and subtract this value from minus b over 2a. That's how we get these two distinct values. One of them is where we add this second fraction, and the other one is where we subtract the second fraction. We're always going to get two distinct solutions because, remember, this second fraction, as we said, was not equal to 0. Let's try and look at this from a graphical perspective. Again, here we are, we've got two solutions clearly for this quadratic. Remember, our line of symmetry is what that first fraction was in green, x equals minus b over 2a. We're going to be adding on the second fraction over here, and we notice that this is how we get one of the solutions, and the other solution is going to come from when we subtract that second fraction. And so clearly we're going to get these two distinct solutions. So in a sense, we've sort of clarified why we get two distinct solutions for when the discriminant is positive. Let's now look at when the discriminant is equal to 0. We said we have one repeated solution. Let's have a look at this quadratic, which clearly has just one solution if I draw it on Desmos. If I substitute in the numbers, I get b squared is the square of minus 4. I subtract 4 lots of, again, the 1, the invisible 1, multiplied by the 4 at the end. This simplifies down to 16 minus 16, which is definitely equal to 0. And we can see, therefore, that if a quadratic has one solution, then the discriminant is definitely equal to 0. And you could have possibly noticed this from realizing that I can actually just complete the square on this quadratic, and I get x minus 2 all squared, which is of course just a shift to the right of the simple quadratic x squared. Alright, let's try and again reinforce this. Splitting it up into two fractions, we have that if the discriminant is equal to 0, then all of this fraction will become 0 because we're square rooting 0, because b squared minus 4ac is 0. We square root that, we get 0. We divide it by 2a, we're still going to have a 0. And so that this whole second fraction, this red part, must be equal to 0. And so we are adding and subtracting 0 from this green fraction. And of course, that's not going to change it at all. So it means that the only solution must be at this number, i.e. on the line of symmetry. And again, let's look at this graphically. There's my line, x equals minus b over 2a, again the line of symmetry of the graph. And since we said that this second fraction is equal to 0, we're not going to have any arrows like last time, because we're not going to be moving anywhere, right or left. We're going to be right here in the center, and there's only one solution. And so hopefully you can see that there's only going to be one solution when the discriminant is equal to 0. And finally now, let's look at when the discriminant is less than 0. We of course said we have no real solutions, but again, let's try and think about that in a bit more detail. Let's have a quadratic, x squared minus 3x plus 3, which clearly has no real solutions when I draw it on Desmos. If you don't trust me, please go ahead and type y equals x squared minus 3x plus 3. You should get something that looks like this. And you'll notice that it doesn't have any solutions at all. Again, let's quickly substitute these values in. You square the minus 3, you subtract 4 lots of 1 multiplied by the 3, and of course you get 9 minus 12, which is definitely negative. And so we've seen that when there's no real solutions, the discriminant is going to be negative. But again, let's try and see why this is true. If the discriminant is less than 0, we're trying to find the square root of a negative number. This is not possible on the real number line, because you can't square root a negative number. Try it on a calculator, it won't give you a real number. Hence we say that this yields no real solutions. For example, try to solve x squared equals minus 1. Of course you'll run into problems, but if we were allowed to use complex numbers, we'd be okay, but of course we aren't allowed to use complex numbers yet. Okay, let's try and put this into practice. Let's try and do a few examples. We'll start off with x squared plus 2x minus 1, and of course as always, if you're feeling confident, go ahead and gallop ahead and try these yourself, and try to get to the solution before I get there. So the first thing we're going to do is we're going to write out separately what each of the values are. So a equals 1, b equals 2, and c is of course minus 1. Substituting the numbers in, we get 8, which is definitely bigger than 0. Therefore, we must have two distinct solutions for this particular quadratic. Let's have another one. This time, just like previously, we're going to write out our values. A equals 2, b equals minus 3, and c equals 2. And then we're just going to substitute the values in to our expression for the discriminant. Make sure you use brackets around any negative values, especially. It's a common mistake I see a lot. Don't do that. It's not good. You're going to expand this and simplify, and of course, you get a negative number because you have 9 minus 16, which is less than 0. Therefore, we can see that this quadratic has no real solutions. And of course, if you want to double check that, go ahead and type y equals 2x squared minus 3x plus 2 into Desmos, or any graphical calculator you can get your hands on, and you'll see that it has no real solutions. It doesn't touch the x-axis anyway. Right, for the final example then, the first thing you want to do is rearrange this into a format such that it looks like ax squared plus bx plus c equals 0. And then, again, we write out our a, b, and c. Substituting this in, we get the following. And of course, this equals exactly 0 because we have 36 subtract 36. And then finally, we can say that this is definitely just going to have one repeated solution. And you can probably see this just from here. You can see that this is going to be x plus 3 all squared. So it's just a shift to the left by 3 units of the quadratic x squared. So it's definitely going to be just sitting on top of the x-axis, and hence one repeated solution. You'll find questions similar to this in the homework exercise 1.1, which you'll be able to find in the description box. So please make sure you do that. Let's have a look at another example. This one's going to be a little bit tougher, and this one's going to be making use of what we've just learned in the previous section. Use the discriminant to prove that y equals 4x is a tangent to the curve y equals x squared plus 2x plus 1. They've used the word tangent, and what they're implying here is that the line and the curve meet exactly once, and this indicates a repeated solution or a root. So look out for that. The word tangent represents a repeated solution or a repeated root. Sometimes they use the word root instead of solution. It's good to know that they mean the same thing. This is going to be at the point of intersection of the two graphs. So we're going to have something that looks like this. This one in red is y equals x squared plus 2x plus 1. And this straight line is, of course, the linear graph y equals 4x. Some key things to note are, if the graphs do not intersect at all, there are no solutions, and so the discriminant must obviously be less than 0. In other words, b squared minus 4ac would be less than 0. If, however, the graphs intersect twice, there are two solutions. Therefore, the discriminant must be greater than 0. In other words, b squared minus 4ac is bigger than 0. Combining the two equations, we get 4x equals x squared plus 2x plus 1. We're just going to quickly rearrange this by subtracting the 4x from both sides. And so if this new quadratic x squared minus 2x plus 1 has a discriminant of 0, then we're done. Because remember what a discriminant of 0 meant. A discriminant of 0 meant that you have one repeated solution, and that's exactly what we're aiming to prove. That's what the tangent meant, remember? So let's quickly check. A equals 1, b equals minus 2, and c equals 1, of course, in this quadratic. Substituting those values in, we get an output of exactly 0, and that's exactly what we wanted to prove. And therefore, this quadratic has one repeated solution. If you want a bit more convincing, what we can say is that let's take this equation again. Let's now set one side equal to 0. Let's factorize. And of course, we get x equals 1 by taking the square root. This implies a repeated root, because there's only one solution here. We literally can see the one solution. It's just 1, and that's it, nothing else. You'll find questions similar to this in the homework exercise 1.2. Again, make sure you try it. Now we'll look at the next bit, which is going to be on inequalities and discriminants. The first example we'll look at is this equation has no real solutions. We're asked to find the range of possible values of k, and we have to give our answer in set notation. Let's start with this equation, and of course we always want to make it equal to 0, so let's subtract k from both sides. And at this point, because it says it has no real solutions, we have to have that the discriminant is less than 0. Make sure you've ingrained this in your mind at this point. And substituting these values in, b equals k, and the c, the constant term, is just going to be the 8 minus k. Expand and simplify, we get this inequality here, and of course factorizing gives us this bottom inequality here. Now remember, when we have an inequality, a quadratic inequality, we want to ideally sketch the graph so that we can visualize which solutions we want. Let's draw the graph of this. We can clearly see that it's going to have two solutions, one at 4, 0, one at minus 8, 0. And since we actually wanted this quadratic to be less than 0, we want the parts where the red curve is below the x-axis. We want the numbers between minus 8 and 4 exclusive. Exclusive because this is a strict inequality. We don't want to include the endpoints, minus 8 and 4. Okay, so let's go back. We can therefore say that this implies that k must be between minus 8 and 4 exclusive. And in set notation, this would be the intersection of two sets. One of the sets containing all the real numbers greater than minus 8, and the other set containing all of the real numbers less than 4. Simply, you could write this as the set containing all the real numbers between minus 8 and 4. You could actually combine this into one inequality. Both solutions are fine. For the next example, let's look at where this equation has equal roots. Find the possible values of m. The first thing we're going to do is take this equation and realize that the equal roots here is implying that the discriminant is equal to 0. Equal roots just implies that it has one repeated solution. That's something to bear in mind. So just like how we had tangents earlier, and we said that also represents one repeated solution, so does the phrase equal roots. Let's now substitute the values into their appropriate places. Let's expand and simplify, and then let's neaten that up a little bit. And we notice that we can actually divide this all by 4. Let's do that. And now we've just got a nice, easy quadratic equation to solve. And I'm just going to use the quadratic formula at this point, because I can't really be bothered to factorize. Let's use the quadratic formula, substituting the numbers again into their appropriate places, and I get two solutions. And I can simplify this because square root of 52 is equal to the square root of 4 multiplied by the square root of 13, and that would cancel with the denominator, and I get 4 plus or minus the square root of 13 as my two solutions. So for these two values of m, this equation has equal roots, i.e. it only has one repeated solution. If you have any questions about any of this, again, make sure you're asking. Another example, this time we have an equation, k is a constant, and all we know is that it has some roots. We're asked to show that this inequality is true. So again, we'll start off by realizing that when it says has real roots, it means that it either has one or two roots, but definitely not 0 roots. Okay, so the discriminant will either be exactly 0, and that's when it has one root, or it'll be greater than 0, and that's when it has two roots. But the discriminant definitely can't be less than 0, because that would imply that the equation has 0 roots. So in other words, our discriminant, b squared minus 4ac, is going to be greater than or equal to 0, because it could have had either one or two roots. So in summary, has real roots implies that the discriminant is greater than or equal to 0. Now realize that at this point, I want to ensure that my equation is in the form ax squared plus bx plus c equals 0. So let's quickly do that. So the a is the 2k minus 3, the b is the 2, and the c is just the k minus 1 here. Let's substitute these values in. Let's expand and simplify. Take everything to one side. Let's divide through by 4, and we get exactly the inequality that was asked of us. And we're done. The second part of this question asks us to find the possible values of k, giving our answer in set notation. So basically, solve the inequality. So let's start again with this inequality. We're going to factorize. And once we've factorized, we realize that a good idea is to draw a quick sketch, just like what we did in example 1.3. And that helps us visualize this and see the solutions a little bit more easily. And when you do that, you'll realize that again we have an intersection of sets, where one of the sets is all the real numbers greater than or equal to a half, and the other set is all the real numbers less than or equal to 2. Please feel free to check if you're not convinced. And you can of course write that a little bit more simply. You can write it like this here as well. In our next example, we have a curve with equation y equals 2x squared minus x minus 1. We have a line that has the equation y equals k lots of 2x minus 3. K is just some constant, and we know that these two intersect at two distinct points. Okay, straight away, two distinct points tells me that the quadratic that I form from these two will have a discriminant greater than 0. We're asked to find the possible values of k, so the first thing we want to do, since we know that the graphs intersect, let's equate them and simplify. So we set the curve equal to the line, we expand and move everything to one side, and then we're just going to try and, again, put it into the format ax squared plus bx plus c. Now also, in the question it said that the curve and the line intersect at two distinct points. This of course means that this simplified equation that we have here from the previous little section has exactly two different solutions in x, of course, as we already mentioned, and so the discriminant of this quadratic is strictly greater than 0. In other words, b squared minus 4ac is bigger than 0. Now, if I take the simplified equation that we got in the previous segment, I substitute the values into my inequality for the discriminant into their appropriate places, I have this here. I'm going to expand, simplify, and collect like terms. I simplify into 4k squared minus 20k plus 9 is greater than 0. The next thing to do is to factorize, and if you need to draw your sketch, go for it. And you should realize, since this is greater than 0, we're going to have the arms of the quadratic, if you like. And so we're going to have two disjoint sets. And so we need the union of these sets. One of them contains all the real numbers less than a half, and the other set contains all the real numbers greater than 9 over 2. Again, remember to try the exercise questions to consolidate this work, but we'll move on to the next part, the final part of today's lesson. So the third part is about reciprocal inequalities. We need to recall from GCSE that when we multiply an inequality by a negative number, the direction of that inequality changes. This can sometimes be a bit problematic when multiplying by a variable, because that variable can be positive or negative. What we do instead is we limit ourselves to only multiplying by variables which we know must be positive. And now you're probably thinking, how are you going to force a variable to be positive? Well, we've been talking about squares this whole lesson, and you might realize that if I multiply by the square of a variable, I won't have to change the direction of the inequality, because a square can never be negative for real numbers. So, first example, let's find the range of values for which 7 over x is greater than or equal to 28. The very first thing I want to do is multiply by the square of whatever the denominator is. So I'm going to multiply by x squared, and I get 7x on the left hand side and 28x squared on the right hand side. I'm then going to subtract the 7x from both sides. I'm just going to ensure that the 0 is on the right hand side. Then I'm going to divide through by 7, because we're allowed to do that. We're dividing by a positive number. There's no issue with doing that. And then I'm going to factorize. And then at this point, again, I'm going to think about my graphical sketch, if you like. And you'll realize that you get something like this. So x is between 0 and a quarter inclusive. But I want you to think really carefully about this part of the inequality. Can x actually be 0? Am I allowed to put 0 as a denominator? Something to be cautious about is you'll need to exclude a possible solution, because the denominator of a fraction can't be equal to 0. So we're just going to exclude the 0 by removing the equal symbol there, and we're going to be left with just this inequality here, and this is the range of values for which this inequality is true. We'll do a similar thing for this question. I'm going to multiply not by p squared, but again by the denominator squared. So I'll multiply by the square of p minus 2. So on the left hand side, I get 3 lots of p minus 2. On the right hand side, I simply get p minus 2 all squared. I'm going to now subtract, just like I did in the previous example, and I'm going to ensure that the 0 is on the right hand side. And this is what causes the inequality sign to flip. I'm going to now factorize. I'm going to pull the p minus 2 out the front, and I'm left with one of the p minus 2's, subtract this 3 here, hence I have this, which can simplify a little bit down to p minus 2 and p minus 5. Now think about the graphical sketch, and we want either p to be less than or equal to 2, or p to be greater than or equal to 5. But again, remember, we cannot have this denominator equal to 0, therefore we restrict p and don't allow it to equal 2. Hence, we remove this equals here, and we have this as my final answer. P is less than 2, or p is greater than or equal to 5. And you can go ahead and substitute some numbers in and see if that does indeed hold. You'll find questions similar to this in the homework exercise 1.4, so make sure you try them. You'll be pleased to know that this is the final example of today. So we have a rectangle, the width is shorter than the length, and the area is less than 456 centimeters squared. What we're asked for is the possible values of b. So we'll start off by using the first fact, that the length is greater than the width. We have that 5b minus 1 is bigger than 2b plus 9, and of course a simple and quick rearrangement to solve leads us to b is greater than 10/3. Second bit, we'll look at the area being less than 456 centimeters squared. We must have that the product of these two dimensions, the length and the width, must be smaller than 456. Let's expand, simplify, and make the right hand side equal to 0. Now factorize. Of course, you don't have to necessarily factorize. You could just solve it using the quadratic formula. You could set the expression 10b squared plus 43b minus 465 equal to 0 and solve using the quadratic formula. But you can also factorize. So let's just work from there. So at this point, making use of a sketch, we can see that the solutions would have to be between minus 9.3 and 5. So combining the inequalities now from parts 1 and 2, so combining the b is greater than 10/3 and this inequality that we just got right now, we can see that the range of values of b must be between 10/3 and 5 exclusive, because we're looking for where both of these two inequalities are true, and that is only in this small range of values here. And that's the end of the lesson. Just make sure you're trying out all the exercises, and of course, if there's anything that you're struggling with in particular, make sure you ask. In the description box, make sure you find the answers to the workbook that was available in the previous video, and also you'll find the homework questions that I've been alluding to throughout the video. So please take care, have a good remainder of the day, and I'll see you in the next lesson. Thank you and goodbye.